Okay, so let us continue now. So what we want to talk is this, the notion of factor group, sometimes called quotient group. Okay, so let me, you can see it in the slide, but let me just explain it on the board, yes? So what we learned before the break was this. We have a group, but we have a normal subgroup. And then we learned that if I if I collect all left cosets of this subgroup here, then the star, which we define it in this way, AH star, we don't need to even put a pair of brackets, BH is equal to ABH. I hope that I could convince you that this is a well-defined binary operation on this set, which I called it back then capital M. But now I told you that there is more standard notation for it. This is the set we noted. So from now on, if you see this notation in abstract algebra, what do you immediately understand? You understand the top one is a group. You understand the one below is a subgroup, but more than that, it's a normal subgroup. Otherwise, this doesn't make sense. You can go, and if you want, you can go home and see that if H is not normal, this binary operation is not well defined. Okay? So this is something you can go and check yourself. But whenever in abstract algebra you see this notation, it means the top one is a group, the one below is a subgroup, but it is a normal subgroup. And then this operation defined on that, which in your book you don't even see this star. So you see it in this way. But this operation between A and B is the group operation. But this operation that you don't see is the same star we just defined before the break. Yes, that's the mean. Okay, now we want to, this theorem, is it theorem 3? Yes. So theorem 3 claims that, GH and that star is a group. Okay? So, to prove the group, we have to be sure about 4 things: closure, associativity, and then identity element and the inverse element, something like that. Okay, but is the closure was the previous theorem actually. Yeah, so it was a well-defined binary operation. If it is well-defined, it is clear it is closed. Why? Because this is also a left coset. So I am going back to my set again. So closeness is clear. What was not clear was that this operation was well-defined, which in the previous theorem we guaranteed yes. Yes, you can sleep well. It's well-defined. But now if I go to the next step, I want to prove associativity. So can you help me? I want to prove that this group under that binary operation up there is associative. So how should I prove that? I want to prove the binary operation is associative. So how should I prove that? It means I have to convince you that this star BH star CH is equal to what? AH star BH star CH. But I hope that you agree that this is correct, yes? Associativity of this operation boils down to the associativity of the original operation in the group. Why? Because if I ask you what is the left-hand side, I don't want to completely prove it because it's very simple. If I want to calculate the left-hand side, I have to do this one first because it is prioritized, so I keep it for the time being. A star, and then what is the answer to this one? Is BCH. Do you agree? And now I want to do the same operation again. What happens? It becomes this one multiplied by that. But now this one is at the level of the original mother group. Yes? So I can do it. I can do associativity here. And then then I can open it up. Hopefully you can do it in 2 steps, of course. Yes. And then this becomes equal to okay. But because this is more or less trivial, I'm asking you about the identity element. Can you tell me which one of these elements play the role of the identity element of the factor group?
Same one as G?
No. The elements of G and factor group are different things. So the elements of G are atomic elements, G1, G2, G3, but the elements of the factor group all are cosets. They are sets. Okay? So you cannot say the same, they are related, but you cannot say that the identity of this group is the identity of the mother group, because they are different in character. You understand what I mean? The items are not the same, the elements are not the same at all. But there is a relation. Can you guess what is that?
So it's EH.
EH. But what is EH? Do I really need to write EH? It is H itself, because when you write EH, it means E multiplied by H for every H in H. But this is nothing except H. H belongs to H, and no one writes like that. We just simply write H, yes? Okay, so hopefully you agree that H itself is one of the elements here, and it will play the role of the identity element of this one. Okay? But now, one more thing. What is the inverse? If I give you an element in the factor group, what do you think will be the inverse of this? The inverse is what? The inverse is something that is multiplied, this one gives me the identity element of the group itself. But we just learned the identity is H itself, okay? So what does it mean? If I want to answer the question mark, so the question mark, so let me write the question mark is X I am looking for, H. Okay? And then let me multiply it by this one. So XH star AH should become equal to the identity element, which is EH or H. Let me write this one EH. I have some reason why I'm writing it like that. Yes, do you agree? This is what I want to prove. This is the question mark I'm trying to answer. But help me to answer. The first thing I do, I will do this operation. What's that operation? It is XAH. And the operation, so I just copy and paste EH. But I forgot, I cleaned everything. But do you remember, if I have one left coset equal to another left coset, this happens if and only if what happens? The inverse of that multiplied by that belongs to H, yes? It's not a good way, Yeah, might be it's not a good way, because you can immediately guess. I am making it so hard, sorry. Yes, could you guess what X is?
A inverse.
Yeah, X should be A inverse, yes? So you can say that claim X is A inverse, this is the proof. It's easier, yes? Because then when you multiply A inverse by A, it gives me exactly this. That's better. So that's it. So what did I do? I have one group, I have a normal subgroup. Using these two, I made another group. Yes? Is that clear what we did? So that's the quotient group, and I want you to somehow remember it because that's part of your course as well. Okay, if you don't mind, do this example yourself. It's very simple. But I just want to ask you one question. Does this notation make sense? Because you cannot just randomly write a group divided by another group. If you want to use this notation in algebra, the top one should be a group, the bottom one should be a subgroup, but more than that, it should be a normal subgroup. Is that right? So I just want to ask you, do you think that this notation makes sense? Is this a group?
Yes.
What was the group? The elements are 0, 1, 2, up to 17. What was the operation of the group, which is not mentioned? I told you by convention. When I don't mention it here, it is the addition, modulo 18. And this is the group subgroup generated by 6. Okay, what is that?
0, 6.
Yes, 0, 6, and 12. Okay? But still it is not guaranteed I am allowed to use this notation. For using this notation, I need more.
It is with normal.
This is a subgroup that is guaranteed, but that is not good enough. I need a normal subgroup. But is it a normal subgroup? Yes? It should be, otherwise my slide is wrong. Okay, no. That's a political way to answer my question, yes? But do you remember what this group is abelian? You remember one example I told you as an example, but I asked you to remember that any subgroup of an abelian group is automatically normal. Yes? So this is a subgroup of an abelian group, so it is automatically normal. So everything makes sense, so this makes sense. Okay? So for example, one element, can you tell me what are the elements here? What is the identity element of this group? You answered here. The identity element is H itself. So what is the identity element here? This guy. Okay? And what are the other elements? So you can write 1 plus 6. Yes? What is 1 plus 6? What is 1 generated by 6? It means add 1 to each one of them. So it is 1, 7, and 13. Yes? So in principle, this is a set of sets. Those sets are points in this group. Is that understandable? Okay, so that's it. And then can you tell me the next one is 2 plus 6? Can you tell me until where I should go? 5 plus 6. Because if you continue more, you will go back to the previous one. So that we did it actually. But if I did it quickly, you can go home and think about it yourself. So what happens is that this is, if you want to have an imagination, if here the elements are numbers or atomic elements, 0, 1, 2, 3, etc. But as soon as you have this, you have a set of sets. So the elements are sets themselves. So that's important to have it in mind. Is that understandable? Okay. So now we go to the very important topic of homomorphism. Homomorphism and the fundamental homomorphism theorem. Okay. So this is definition of a homomorphism. Don't say homeomorphism because then it will be in topology. Yes, you should say homomorphism. So what is the meaning of homomorphism? You have this slide, but if you don't mind, let me explain it here on the video. It's very, very similar to isomorphism, but with some conditions relaxed. So can you remember what was isomorphism? What was the definition of isomorphism? Yes?
There exists some bijective function from
which preserves, yes.
Which what was it? It preserves the group
Structure, operation, exactly as you see here. So the only difference between homomorphism and isomorphism, so isomorphism is a special case of homomorphism. So if I give you two groups, what group 1 with its own binary operation and group 2 with its own binary operation. Yes? So F, what did I use F? F from G1 to G2 is called a homomorphism if it only cares about group structure of the operation, meaning that for every A and B that you choose from the domain group, F of A star 1B becomes F of A star 2 F of B. That's exactly the condition we had for isomorphism. But for isomorphism, this function should be injective and surjective. We don't need it here. Okay? So if we have only this group structure reserved, we call it an homomorphism. Is that clear? So can you define for me the isomorphism in a way that you can have the word homomorphism in its definition? Because in some algebra books, I am following the order in your book. The book has talked about isomorphism first and then homomorphism. Okay? But some books we can talk about homomorphism first and then restrict it more, then it becomes isomorphism. Okay, if I want to define an isomorphism, that's just a intellectual practice, you know. If I want to define isomorphism that we did before, in a way that I can have the word of homomorphism within its definition, yes?
Bijective homomorphism.
Yes. So a bijective homomorphism is an isomorphism. Is that clear? You have to play around, yes? So that you remember these things. Any question here? Okay, but there is one new concept so let me, by the way, define what does it mean. If I have a domain group G1, for example, if I have element and then I have a codomain group G2, and then I have an element here, this F will take A to F of A. Yes? And then, for example, if I have a B here, and this will take me to F of B, which is there. If I want to do an operation between them, the operation between these two should be operation of the domain group. If I want to do an operation between them, the operation between them should be the operation of the codomain group. Is that right? Okay. But now, let us say that I do this, I do the operation between them, and it turns out to be C. Okay? C will take me to FC. But what is the relation between FC? So this is group 1, this is group 2. Something like that. I don't know if this is making it simpler. Yes, so it might be the definition is more simple. So what I'm saying is that if you have if you do the operation between these two and get C, then if you do the operation between the images of these two, you will get the image of C. Something like that. Okay? But what is the kernel? Kernel of so kernel, first of all, makes sense not for every function. Kernel makes sense if this function within is a homomorphism. And what does it mean? It means the set, what I have written X, the set of all X's in the domain group whose image is the identity element of the codomain group. So it means that F takes those X's to E2. Yes? So if you want to have a picture in mind, if the picture is not making it more difficult, so here you have E2, one of these elements. So the collection of all these elements that all of them are going to this is called the kernel. This yellow part is the kernel. Is that right? The collection of all elements in the domain that are mapped to the identity element of the codomain group. That's called the kernel. Any questions? Okay. So let us understand this a little bit more. Oh, okay, I have written it here. An isomorphism is a homomorphism, but we did it before, so let us rush a little bit. This one. Example 5, consider this group. Is phi defined in this way a homomorphism? If so, what is its kernel? It's a very standard example to make this understandable. Okay, so let us do it on the board. Example 5. So I have given you a group, R star. Do you remember what was R star in this course?
It was real numbers apart from 0.
Apart from 0, do you agree that this was a group under normal ordinary multiplication? Okay, so this can play the role of the domain. In this example, my codomain is also the same. And I am defining a function phi from R star to R star, and I have told you what does it mean. It means that phi of x is just absolute value of x. So the problem is asking, do you think this function that I have defined from a group to another group, which in this case is the same, by this definition, do you think it's homomorphism? If the answer is yes, find its kernel. Let me ask you one question, because we already learned. Is this an isomorphism? No. Why? You remember this is like the graph of this is like that, and this is not one-to-one. So it is already we know that this is not isomorphism. But is it homomorphism? We have to check. Okay? How should I check? I should say that let x and y belong to R star. What is R star? R star. Let me write R star because you know R star. Okay? We want to show that, we want to check this. Is this the case that if I multiply x and y and then apply phi on it, it becomes equal to phi acts on x, phi acts on y, multiply them. I want to see if the results are the same. So if you want, this operation is here, and because the right hand side is the same group, so that one is also the same. Okay, do you think this is correct? Let us check it. Yes or no? What is your intuition? And there is no intuition, just calculate it in a matter of seconds. So how should I calculate it? Left hand side is equal to phi xy. But what is phi xy? Phi takes a number to its absolute value. So takes this number to its absolute value. But do you remember in high school that absolute value of a product is the product of absolute values? And if I ask you what is absolute value of x, it is nothing except phi x. And what is absolute value of y? It's nothing phi of y, and that is equal to the right hand side. So this is your homomorphism. Simple as that. But is this what is the kernel? As soon as I have a homomorphism, then I can talk about kernel. So the kernel is not something I can talk about any function, but homomorphism. So can you tell me what is the kernel of phi? Let me write the definition. Help me to write the definition. I would say the set of x's belonging to where? To the domain group, R star. Such that what happens? Phi of that x becomes the identity of the codomain. But in this case, codomain is also R star. And the operation was multiplication. So what was the identity in the codomain? 1. So this is it. So you want to solve this equation. I mean, you want to specify this set. In order to specify this set, we do some copy and pasting here. But instead of this one, I am allowed to write absolute value and copy and paste. So you should be a very good copy paster in mathematics, yes? Because every time you just go a little bit forward. Okay, and then what can I write for this? I am looking for all non-zero real numbers so that the absolute value is 1. There are 2 of them.
Plus minus 1.
Plus and minus. So that's also your kernel. So this is a very simple idea. Okay. One of the very important theorems now. So these ones I have put as checkpoints. Please do them. They are very simple. You see, this is not hard at all. But this theorem is a good one. We go through it together. But might be I can skip part D. You can do it as an exercise yourself. It's good to remember them. Do you have questions? Okay. So if I have, let me explain it here on the board so you can see it in the slide. So it is theorem 4. So what do I have? I have a homomorphism. And for simplicity, let me write home here. So F is a homomorphism. And then kernel, so K, for simplicity, instead of writing K-E-R, I have written K. K is the kernel, and R is the range. Range. Okay? So, if I want to give you a picture, this is G1, this is G2. Where is kernel? Kernel is somewhere here. Yes? By the way, can this kernel be as big as the original group? Yes? So let me write it K. Yes? So this can be, so this is also a good exercise. So I have asked you to solve it in your home, exercises. And where is R? R is also in the codomain. Okay, so something like this. Okay, so I have a group homomorphism from a group structure to another. If you determine its kernel is here, its range is there. So the theorem claims four things. The first thing is that it maps the identity of G1 to identity of G2. So the first part is F acting on E1 gives you E2. It was like isomorphism. Do you remember isomorphism had this property as well? So part B, what is it claiming? It's claiming that for every A in the domain group, F of A inverse, this inverse is with respect to the operation of the domain group, is equal to F of A, which is something in the range, inverse. So these inverses are with respect to different operations. This is with respect to the domain operation, this is with respect to the codomain operation. That was also shared by isomorphism. So I will not do these two, so these are very simple ones. Okay, but one thing you need to know, for the time being, this one is a subset. We go one more step, we say that it is a subgroup. We go one more step, we say it's a normal subgroup. Okay? This is what we want to prove. So in part C, we want to prove that the kernel is a normal subgroup of the domain group. But this one only promotes up to subgroup, not to normal subgroup. Yes? So this D, the range remains a subgroup. So let me emphasize here, okay? I only want to prove this one for you, and then you can work on the other ones yourself. So how can we prove this one? Help me. Prove part C. I'll give you 2 minutes to think. How can I prove that K is a normal subgroup? The first thing you need to remember is what? Can you tell me at least? What are you trying to remember? Yes?
Maybe that G1 is abelian.
What?
That G1 is abelian.
Is what?
Some abelian, maybe? Abelian?
A build room?
No, it's a abelian.
No, because it is not mentioned in the problem.
Okay.
No, might be you're confusing this. I didn't say that every normal. I mean, so I said this. If you have an abelian group, then every subgroup is normal.
Right.
Okay, this I told you. I agree, but nothing is mentioned about if G1 and G2 are abelian or not, but still, if you trust me, the theorem is valid. So it means the proof is not probably going through proving abelian. Okay? So if you want to prove this one, and I'm just telling you how to think in mathematics. For example, I want to prove this because these theorems are, even though they are mentioned as theorems, but they are very easy. Yeah, I mean, if I give this in the exam, you really should be able to do it, not say, oh, this is theorem, I cannot solve it, I cannot prove it. No, because this is even easier than many of the problems. The problems in the home assignments are much harder than this one. So whenever something is theorem, it doesn't mean immediately it is hard. Okay? But especially in linear algebra, in abstract algebra, in analysis, it might be hard sometimes. Okay, but here, if I want to prove that this subgroup is a normal subgroup of this one, the first thing I ask myself is what is the definition of a normal subgroup? Okay? And the second step is that I know the definition. Either I start with the definition here, but if I want to be a little bit more optimized mathematician, I would say that is there some easier way to prove the normality without going back to the original definition? This mind structure you should have as a mathematician, yes? But do we have something like this? Yes, do you remember what was it? It was this structure. Let me write it here. Yes? So either you can go completely back to the original definition, which is not optimal way of doing mathematics. You shouldn't go always start from scratch, but it is better to start from here. Do you agree? So now that you remembered, can you start the proof? What I would say, I want to prove this one, but instead of H, here the notation is what? K. But you need to write one sentence if you want to write mathematics, especially in the exam. So what should I start with? I would say say something?
X in
Very good. X is
G1.
G1. We show that is not necessary for math articles, but in pedagogical way, it is better to write. Okay? So in the exam, if you don't write, I will not actually deduct any points because I am used to reading that way. Okay? So let X belongs to G1. We show what? XK X inverse is a subset of K. Yes? So this in principle you should write it. Some students start from here and put it on me to understand what X is. So when I bring X, K is already defined, so you don't need to define it here, but you want to bring X in. So you have to say what X is. X is nothing except the group from X is from G1. Now I want to prove this one. How should I prove this one? Then you write. So I want to prove this statement. You say let again. You want to prove something is a subset. So you say let
K belongs to, or lowercase k belongs to uppercase k. Just like,
yes, but let me choose another letter to not be confused because K is a little bit tricky. Okay, for the reference. So I would say let alpha belongs to what?
k.
X, no, belongs to this one. We prove,
That is also a K.
yes, we prove alpha belongs to K.
Yes.
Is that right? Okay. Now, this is the mindset you have to develop. Don't start manipulating your assumption. You want to prove this. The first question I ask myself is my goal is to prove this. I have this at my disposal, I know, but my goal is this one. In order to prove that alpha belongs to the kernel, what I need to prove? This is the first question I ask myself. If I can do it directly, I don't even care what I have. I just start doing it. But if I cannot do it directly, then I go back to my assumption to use it in some way. This is a good structure you should make it in your brain. Then it becomes automatic for you and it becomes more optimal. So I want to prove alpha belongs to kernel. What should I prove? I ask myself, this is my goal. How can I achieve the goal? By showing
But f of alpha
f of alpha is
E2.
E2. Okay? My goal is clear. So this is the way you think and then you can write it better. So you write something like this. This is equivalent to proving that f of alpha is equal to E2. Okay? So, but then I want to apply f on alpha. I don't have alpha because this alpha is not equality. I want to apply f on alpha. I need to know what alpha is. Okay? Yes, please.
You can use the definition of f
Yes.
I think it's B there.
Here.
Yes.
Yes.
So f of
No, don't jump ahead. That's correct. This will come in.
Okay.
But don't jump ahead. So this is the way you think. Alpha belongs to K. I ask myself what I'm supposed to do to prove this. The answer is simple. I have to prove that f alpha is E2. But I want to apply f of on alpha. So I need alpha equal to something. But alpha is not equal to something. Alpha belongs to something. But that is easy. I want to make it equality. So what I would say? I would say that now, since x alpha belongs to x k X inverse, then there exists a little k in K. This is, by the way, not good, so you need to write it in words. There exists a k in K such that what happens, alpha is equal to xk x inverse. Do you agree?
Yes.
Now, belonging relation changed to equality relation. So therefore, what can I write? I can write f of alpha is equal to f of that combination. Yes? And then what I have a homomorphism. So f of the product is the product of the f's. So this becomes f of x, f of k, f of x inverse. Now what you said is relevant. Yes? So don't be in hurry. So I can write it as f of x. I cannot do anything with that, but I can do something with this.
Det becomes E.
It's E because K itself is coming from kernel. So F, this one is just E2. Yes? And this one is this part of the theorem you mentioned. Okay, so this becomes E2, F of X, totally inverse. And then everyone agrees. What is the answer?
E2.
E2. And that's it. So you have to, if you develop this mindset, especially as abstract algebra theorems, most of them are not hard. So you really know where to start from. And if you develop this habit, this is always useful in every part of mathematics. Any questions? Okay. So now let us go to the next one. This is a very, so hopefully we can manage this one in a good way. But there is one part that I will not be able to cover, or might be we can cover 15 minutes from the analysis lesson, but that is rings. I mean, you need to know the definition of a ring. Okay, but let us not waste the time to see how much we can continue. So what I want you to understand, this is a very important, as you see it is mentioned, fundamental theorem of homomorphism, or the fundamental homomorphism theorem. Okay, so it's a very bad timing, because I have a little bit of board left and no time left. Okay, but anyway, so what is this theorem telling you? The theorem tells you that if you have, fundamental theorem of homomorphism. I think the book has written it in that way, okay? So if you have a group homomorphism from G1 to G2, homomorphism, and the K is the kernel, and R is the range. R is the range. Okay? This is a very nice theorem. Then we have this. G1 divided by kernel is isomorphic to range. Okay? Okay. But first tell me, whenever you see this, it should make sense. R makes sense. R is the range of a function. It makes sense. And then this notation should also make sense. So this is now you understand, before telling you this, I have to bring up this theorem. Why is that? Because I told you that this notation makes sense whenever the top one is a group and the bottom one is a subgroup, but a normal subgroup. So in the previous theorem, this was guaranteed that the kernel is always a normal subgroup. So I don't have any problems with writing this. Is that right? Okay. So in that case, this is the factor group. And this is a group again. Why? Because this we didn't prove it, but it's a group. So this symbol only makes sense if I have one group on the left and another group on the right. Because this symbol is the symbol of isomorphism, if you remember. This is telling you that these two groups are carbon copy of one another. Is that right? So, and everything at least makes sense. Because this notation should be between two group structures. The right one is a subgroup, so it is a group. The left one is also a group because the K, the kernel, is a normal subgroup. Okay, so we want to prove that these two are isomorphic. Okay, so what do you think we will do? And you know, you have done probably some the last question in the home assignments. It was very hard if I didn't give you the function. You have to come up with the function itself and then prove the function is bijective and keeping the structure. So you have to do the same thing here as well, because the function is not given to you. But you should be able to guess it. It's not very hard, even though it is called a fundamental theorem, and usually they are harder. But I want to trust a little bit on your intuition. Can you guess what we are supposed to do? So I go to scratch paper. I ask myself, I want a phi from where to where? This you should immediately answer. From where to where? From this one to that. Okay, so G1, K to R. And remember, R is the image, is the range. Okay, but what I want to impose on it, I want it to be bijective. Yes, because I want to have isomorphism. And now that you have learned about homomorphism, I want it to be also homomorphism to keep the structure the same. Is that right? Okay, but do you have any guess? So you shouldn't. So what are the elements here? Do you remember what are the elements? G1K are the set of all left cosets of K. So they are G, K's, but where G is coming from the top one. Yes? Is that right? So when you want to define a function from this guy to that guy, phi should act on the elements of this set. So this means that, what do you think I will write here? What should I write? Usually when you have a function, you put x here. Okay? But that x should be something here. The elements here are of this type. You can write x so that x is equal to jk for some g, but this is not something you write. You really write like this. Very good. And then what do you think I will answer? This is the hard part. It's not hard part. I mean, if you develop an intuition in abstract algebra, you know what to do. What do you have in your hand? You started with this homomorphism. This is granted. And then you found the kernel and the range. So if I want to write something here, this something should come from where?
From G2.
From
the range. Yeah.
From R, range. What is the most natural tool in my hand to reach to take myself to range?
F.
F acts from here and takes me to the range. But F can only act on elements of G1.
So G.
So what do you think I will write here?
F of G.
F of G. Is that right? I am not saying that. By the way, the person who actually proved this one was just thinking like that. Okay? So I hope that you understand that there is nothing guaranteed yet. But if I want to come up with a function so that later I am going to prove it is bijective and homomorphism, the first thing I have to do is to come up with the function first. So I have to respect the rules of defining a function. So I know that my function should go from here to here. So phi should act on the elements from here, which is this one. And I know the answer should be something in R. And then I ask myself, what is the tool in my hand to go to R, to the range? And that's F acting on this G. So you might say, no, Babak, why do you say I want to take it with G, I want to take it on G prime? That's also true, but that's a very crazy way of defining. Then people don't connect G prime to this one. So you need to go from something I give you to something definite on the right-hand side. I'm not saying this is done, but this is the most natural construct. Okay? So, we have our educated guess now. What are our duties? Because there is no time, so you have to do it yourself. But might be, let us see how it goes. But what are the things I have to prove for you first? I went to a scratch paper, I came up with an idea. And now the first thing I want to prove is what?
That it's bijective.
What?
That it's bijective.
Not before that.
That it's a function.
It's a function. Why I have to do this? Because this is acting on a coset. I just told you cosets might have different symbols, but they might be the same. Exactly like this f of a of b, okay? So here, well-definedness yes, of 5. This is the first thing I have to do. Okay, might be we can do it later. Let us see. Number 2. If it can survive, it is well defined. The next step,
Bijective.
injectivity. Yes, and the next step, surjectivity. And finally,
That it keeps the
keep the structure. So can you just write the structure? What should I prove? I have to prove that G1K, yes, multiplied by G2K is equal to what? Phi of G1K, phi of G2K. But I hope that you can see that all parts are without creativity if you already know these things. I mean, these are very standard ones. The creativity part of it was to coming up with a suitable function, which is not easy. I mean, I don't remember if I could myself guess that one before. I don't remember when I saw that question when I gave it to you in the home assignment. But that function was not an easy function to come up with if I haven't given you as a hint there. But this is different, even though that was a home assignment. This is a fundamental theorem in abstract algebra. But coming up with this function was more or less intuitive. It was not that hard, unless the most natural way of thinking is not supposed to work. Then it is a catastrophe. Yes? If the most natural one is not going to work, then I really don't know what to do then. So then it means that you have to be extremely creative to come up with a function yourself. But I think this is doable. Okay. My goal is to start, so let me end this recording just here.